Okay, next lemma is let Si belongs to Sn be a simple transposition. Si means it's a simple transposition I to I plus 1. That means I moves to I plus 1 and I moves to I. For example, S2 means 2, 3. Okay, S5 means 5, 6, like that. 5 goes to 6 and 6 goes to 5. That's all. So Si be a simple transposition in Sn and sigma be any permutation in Sn. Then we have to show that number of inversions in the composition sigma Si equal to number of inversions in sigma plus 1 if sigma I is less than sigma I plus 1. Otherwise, it is number of inversions in sigma minus 1. Because we have only two cases. Sigma I never equal to sigma I plus 1 because sigma is 1 1 because it is a permutation. Okay, we assume the case 1, that is sigma I is less than sigma I plus 1. Under the assumption, okay, we have to show that I plus 1 is an inversion for sigma Si. Already it is clear that I is less than I plus 1. So we have to show that sigma Si of I is greater than sigma Si of I plus 1. So what is sigma Si of I? Sigma Si of I is equal to sigma of Si moves I to I plus 1. So this becomes I plus 1. And similarly, what is sigma Si of I plus 1? That is equal to sigma of I because Si moves I plus 1 to I. Okay, therefore, sigma Si of I is equal to sigma I plus 1. By our assumption, that is case 1, sigma I plus 1 is greater than sigma I. And what is sigma I? Sigma I is equal to sigma Si of I plus 1. So conclude that sigma Si of I is greater than sigma Si of I plus 1. That's why this is an inversion for sigma Si. Therefore, this element I plus 1 belongs to I of sigma Si. Okay, actually we have to show that number of inversions in sigma Si equal to number of inversions in sigma plus 1, which is equivalent to number of inversions in sigma Si minus 1 equal to number of inversions in sigma. Okay, so we consider a set like this. We consider the set I of sigma Si minus 1 element. So this collection contains this much of elements, right? Because we know that I plus 1 belongs to I sigma Si. Okay, and what about I sigma? I sigma is nothing. I sigma contains n sigma of elements. So we are trying to establish there is a bijection between I sigma and this set. If there is a bijection between these two sets means number of elements of this set is same as number of elements of this set. Okay, that's the idea. We have to define a function. This function is defined by you take a KL from I sigma, KL from I sigma, then its image phi of KL is defined as Si of K comma Si of L. Our assumption is sigma is less than sigma I plus 1. So it is clear that the pair I to I plus 1, I plus 1 is not belongs to I sigma. Okay. Okay. KL belongs to I sigma means we have three observations. One is K is less than L. Okay. Second one is sigma of K is greater than sigma of L. And already we have seen that I plus 1 is not belongs to I sigma. That means either K is not equal to I or L is not equal to I plus 1. Again, this has further three cases. The case 1 is K comma L not belongs to this collection. That means K and L are not equal to I or I plus 1. And another case is K equal to I and or K equal to I plus 1. Okay, we have to show that in these three cases, Si of K is less than Si of L. Okay, in this case, already we know that K is always less than L. Okay, so what is Si of K? Si of K equal to K because Si moves only I and I plus 1. We assume that K and L not belongs to this set. So Si of K equal to K. And we know that K is always less than L. K is less than L. And what is Si of L? It is L itself because L is not belongs to this collection. So in case 1, Si of K is less than Si of L. Okay, consider case 2, K equal to I. If K equal to I, then what about L? Already we know that L should be greater than K. Okay, so the first possibility is L equal to I plus 1. But we know that the pair I plus 1 is not belongs to I sigma because our assumption is KL belongs to I sigma. So it is clear that L should be greater than I plus 1, right? Si of K equal to Si of I because K equal to I. And what is Si of I? I moves to I plus 1 under Si. Then we know that I plus 1 is less than L, and since L is greater than I plus 1, Si never moves L. So Si of L is equal to L itself. So again we have Si of k is less than Si of L. Similarly, you can also show that when k equal to I plus 1, Si of k is less than Si of L. Because when k equal to I plus 1, we know that L is greater than k. So L is greater than I plus 1. So there is no change for L. When k equal to I plus 1, Si of I plus 1 is I. So of course I is less than I plus 1. That's all. So anyway, all these cases, whenever KL belongs to I sigma, then Si of k is less than Si of L. Okay, so we can conclude that if KL belongs to I sigma, then okay, the first one k should be less than L. This belongs to I sigma means sigma of k greater than sigma L. And extra we have now one more condition, Si of k is less than Si of L. Okay, next we are going to consider what is sigma Si of k. And we know that Si is a transposition. So Si is the inverse of Si. Si itself is the inverse of Si. So Si into Si is identity map. So this becomes k. So that's why this is sigma k. Already we know that sigma k is greater than sigma L. Similarly, we can write sigma L as sigma Si of L. We can conclude that Sik less than Sil and the images of these two numbers under sigma Si satisfies this condition. So we can say that the Sik comma Sil belongs to I sigma L. This is an inversion of sigma Si, right? Okay, now this phi is a well-defined function. Next we have to show that this phi is a bijection. Okay, so first we have to show that this phi is onto. For that we consider an arbitrary element KL from right hand side. We choose a KL from the right hand side. Then we have to establish that there is a pre-image. In this case, we are going to show that Si of k comma Si of L is the pre-image of KL is an inversion. That means k is less than L. And already we assume that this is not equal to I plus 1. So we have two assumptions, k is less than L and KL is not equal to I plus 1. So already we established that under this condition Si of k is less than Si of L. Okay. Already we assume that KL is an inversion of sigma Si. So sigma Si of k is greater than sigma Si of L. Sigma Si of k means sigma of Si of k, which is greater than sigma of Si of L. So we can conclude that Sik less than Si of L and sigma of Sik is greater than sigma of Si of L. So the pair Sik Sil belongs to I sigma. So phi is an onto map. Next we have to establish phi is 1 1. To prove 1 1, we assume that phi of k1 L1 is equal to phi of k2 L2. By definition of phi, this is Si of k1 comma Si of L2. It's a pair, and this is equal to another pair Si of k2 comma Si of L2, and they are equal only when Si of k1 equal to Si of k2. Similarly, Si of L1 equal to Si of L2, and we know that Si's are permutations. So permutations are 1 1. So k1 equal to k2. Similarly, L1 equal to L2. So ultimately k1 L1 equal to k2 L2. Therefore phi is 1 1. So number of elements in I sigma is equal to number of elements in I sigma I minus 1 element. That is n of sigma Si is equal to n of sigma plus 1. So next we assume that k is 2. That means sigma I is greater than sigma I plus 1. We know that Si of I is equal to I plus 1. So this is sigma of I plus 1. And by our assumption, sigma I plus 1 is less than sigma I. And we can replace this I by Si of I plus 1. So the conclusion, sigma Si of I is less than sigma Si of I plus 1. You think about our case 1. In our case 1, sigma is a permutation satisfying this condition. Here, instead of sigma, sigma Si. Sigma Si satisfies the same condition. So in case 1, we are going to replace sigma by sigma Si. So what happened? The left side become n of sigma Si of Si equal to the right side is n of sigma Si plus 1. And we know that Si is a transposition. So Si is its inverse. So Si become I. So inside is sigma. So n of sigma equal to n of sigma Si plus 1. So what is n of sigma Si? That is equal to n of sigma minus 1. That's our second result.